your screen?
Yep. Let's come.
Hey, there it goes. Okay.
Okay, hello everybody. My name is Adrian Hernandez. I'm a first-year graduate student at California State University, Los Angeles, and I'm going to be presenting some research I did over the summer at JPL, and we're going to talk about outer mean motion resonance and how that relates to the production of exodiacal dust. Oops. Okay, so briefly, I just want to touch right away what zodiacal dust is. So zodiacal dust is small dust grains that extend from the asteroid belt down through the habitable zone to the sun's sublimation radius. This dust is believed to be produced by collisions in the asteroid belt, which create smaller dust grains and then are brought inward towards the sun via the Poynting-Robertson drag, and or comets that come close to the sun and sublimate and evaporate and leave behind dust as they do so. And so what's going on here is that the sun is emitting some energy, some light, and it's being absorbed by these dust grains and re-emitted in the infrared, and that's how it can be detected. And I tell you this because this is analogous to what we see in other systems known as exodiacal dust. And exodiacal dust is the warm, hot dust that's detected around other habitable zones. And so what's going on here? Here you see a graph here, and it's a couple of surveys combined of the near infrared excess frequency. And what you see here is that there's a trend showing that it's much more likely to, well, it's the statistics of the occurrence of exodiacal dust detected around near main sequence stars. And so that's kind of odd because in the previous slide I told you that this dust was being created via collisions in the asteroid belt or through cometary evaporation and sublimation. So you would expect that as the age of the system increased, the dust produced by that system would decrease over time, but this is showing that when they took surveys that there was a higher chance of finding this exodiacal dust in older systems versus younger systems, and this is actually what we're going to explore with the rest of the time here. But before I move forward, I briefly just want to touch on mean motion resonance. So mean motion resonance is when the orbital periods of two planets are a close ratio of integers, and it's usually denoted N and P, and in our studies, N is the inner body and P is the outer body. And if you can imagine, one of these is a planet and one of these is a planetesimal, well then there's these mutual gravitational influences between the two. And when you have a larger body such as a planet and a smaller body like a planetesimal, the planetesimal's orbit can be affected as all those mutual gravitational influences add up over time. And so here I show you an image of the solid blue line is the orbit of a planetesimal, and it has some small eccentricity of 0.05. And this this black solid line here is the orbit of the planet and has a eccentricity of 0.1. And this thick red annulus here, that's what is called the chaotic zone of the planet. And so you can imagine that the planetesimal and the planet is in mean motion resonance. Well, over time, if there's enough influence on the planetesimal, well, its eccentricity can be increased such that the periastron of the planetesimal will decrease and enter the outer chaotic zone of this planet here. Now, when this occurs, this planetesimal can either be scattered out of the system or it can be scattered out onto comet-like orbits. And this is actually what we explored via N-body simulations that I'll show in the next couple of screens here. But first, in order to do this, I generated some phase-based diagrams, and what you're looking at here is all these lines here are the total energy of the system, Hamiltonian curves, as they say, and the x-axis is the longitude of periastron, and the y-axis is the eccentricity of the planetesimal. So this is a phase-based diagram when in 1 to 2 mean motion resonance with a planet of eccentricity of 0.1. And here I'm only considering planetesimals with eccentricity between, an initial eccentricity between 0 and 0.05. And the way you want to read this is that you look to the space where you're considering, and you want to follow these lines up all the way to its maximum peak here. And what this maximum peak is describing the maximum eccentricity that a planetesimal can gain when in mean motion resonance of this type, when there's a perturbing planet of this eccentricity. So you can see here in the case of 1 to 2, a planetesimal can reach a maximum eccentricity of about 0.4. And we use this in our analytical predictions coming up here. So what I did was, in Python, I plotted the critical eccentricities as a function of the planet mass. And these critical eccentricities are the eccentricities needed such that the periastron of the planet will decrease far enough to enter the chaotic zone of the planet. And so you see here we have 1 to 2, I plotted here a 1 to 2 mean motion resonance, 1 to 3, and 1 to 4. And the way you want to read this is, well, first we look at what is the maximum eccentricity that a planetesimal can gain when in mean motion resonance of a certain type. And we saw on the previous screen it was about 0.4. Well, we see that the critical eccentricity needed to enter the chaotic zone for this 1 to 2 mean motion resonance is actually lower than that. So what we say is that for all planet masses, we would expect some scattering to occur when in 1 to 2 mean motion resonance with a planet that has an eccentricity of 0.1. Conversely, if you look at this 1 to 4 mean motion resonance critical eccentricity curve, incidentally, the maximum eccentricity induced there was about the same, about 0.4. However, the critical eccentricities needed to enter the outer chaotic zone of a planet are higher than what's allowed. So for these 1 to 4 mean motion resonances, these curves will not allow scattering. And so this is actually where we're going to focus here, since we know that the 1 to 2 mean motion resonance will do a good job at scattering planetesimals. And so what we did was we focused this in our simulation. So this is an n-body simulation here. And it simulates the image that I showed a couple of slides ago with a planetesimal on a planet in an outer chaotic zone. But in these simulations here, we have a test belt of 5,000 particles, which has an annulus of 0.5 AU. We're able to vary the planet mass, but in these simulations, we kept the semi-major axis fixed at 30 AU. And we're able to specify the location of where the mean motion resonance occurs. And on the right here, you see the output. On the y-axis, it's cometary events per year, and on the x-axis, it's time. And cometary events per year are defined as the number of active comets that had a passage below 3 AU. But you can see here clearly, when you have a perturbing planet that has a mass of 0.1 Jupiter mass, when in 1 to 2 motion resonance with a planetesimal belt, well, it does a very good job at scattering these planetesimals, but not only that, it does a good job at scattering these planetesimals over long time scales here. Another thing that I did was I rescaled my rates such that they would copy that of a Kuiper belt analog. And you can see here how the number of cometary events per year increased significantly. And I did that because I wanted to make it something more real, right? I mean, in general, these planetesimal belts have way more particles or way more planet bodies than 5,000. So I rescaled them to look like a Kuiper belt analog. And from here, using estimated dust released by comets as they have a passage, I was able to place an upper limit at a lower limit on the dust estimates based on my model here. And so you see that we're on the order of 10 to the negative 12 megaearths per year for our upper limit, and 10 to the negative 13 megaearths per year for our lower limit. And comparing that to this number here, 5 to the 10 negative 15, this is the dust feeding rates needed to keep the exodiacal dust that we see in our solar system. So we're actually producing more dust, more exodiacal dust than is needed. Something else that I did here was I varied the semi-major axis of the planet. So this top one at 30 AU is what we've been looking at on the previous screens, but then I moved it out to 50 AU, 75 AU, and 100 AU, and you see there's a clear trend for the number of cometary events per year to decrease as you increase the semi-major axis of the planet. But also you see that there's a trend in the delay of production of comets. So you see here, the 50 AU doesn't start till about here, and the 100 AU doesn't start producing comets till about 400 megayear. And another thing that we did in our simulation, well, we added an extra planet between the perturbing planet and the star. And you see here that if you place the one Jupiter mass planet between your perturbing planet, well, it does a very good job at shielding the inner habitable zones. And these two are the same simulations set next to each other, except this has a perturbing, an extra planet in between the perturbing planet, and this one is just that one perturbing planet here. And so what we showed was that when you have a very small undetectable Kuiper belt analog, we're able to produce exozodies after the eccentric planet began to act on the belt. And also if you place a Jupiter mass planet in between the sun and the perturbing star, that it does a very good job at shielding the inner parts from comets. I want to give a real big thanks to my mentor at JPL, Virginie Fermaz. She's been a great help, and the rest of the debris disk team at JPL. And I'll stop and take any questions.
Okay. Excellent talk, Adrian. Thank you very much for that. Again, if folks have questions, please pop those in the session 4 channel on the Slack workspace. I will lead off with one of my own. So looking at the plot you just showed, that 2-planet simulation, what causes the super discrete peaks that you're seeing? So in the one planet, you have this kind of broad, more diffuse shape, and here you have these like very well-defined, short duration events. Can you talk about that a little bit?
Yeah, I think that is a result of the initial amount of particles that I place in my simulation. I think that if I place, maybe I did 50,000 particles instead, that we would see some peaks in between. But I think because of the 5,000 test particle that I started out with, it shows these very, very discrete lines. This is what I'm thinking.
Gotcha. Question from Jason Wang in the Slack. To Adrian, do you know if this enhanced exozody due to an eccentric planet would be detectable with current or future instruments?
I'm not sure, to be honest. I would love to answer that question, but I'm not sure right off the top of my head. I'm sorry.
No worries. Would you expect the addition of if you had additional planets, that you would maintain this kind of protected, inner portion of the orbital parameter space? I'm thinking of the 4-planet systems that Jean-Baptiste was just showing us, things like that.
So like, if I added 4 planets instead of 1 planet in between, will it still do a good job at shielding the inner habitable zone?
Exactly. Do you think there's a magic number, so to speak, of, up to 2 planets is great and protects us, but the minute you get to 3, it all goes crazy?
Oh, that's interesting. I would love to look at that. Incidentally, I plan to run some more simulations, but I'm not absolutely sure. But that's definitely something that's super interesting. If just 1 planet is doing the job, what if you did 4 or 5? What does that look like? That's very, very interesting. Yeah, I would have to run some simulations and look at it to see what's going on there.
Sure. As someone who does not really do simulations myself, what is the runtime for doing these kinds of studies? You set this going, and X number of hours, days, months later, you get results?
Yeah. So if we just took the normal, like 1 to 2 with just 1 perturbing planet, maybe it was like 24 hours. But as soon as we did the 2-planet system, that was almost like 3 weeks. But actually, recently, we found a way to increase the time of running these simulations, which cut down the 2-planet systems from like 2 weeks to about I'm sorry, yeah, 3 weeks to about 2 weeks, but it does get very complicated. But I would say if you run a simple one, it's very quick, 24 hours. But if you run a 2-planet system, it can vary between like 2 weeks and 3 weeks, maybe a month.
Okay, so my 4-planet system might take a while. Understood.
Oh, yeah. Yeah.
Okay, with that, I think we are out of time. So I will say thank you again so much for a wonderful talk. And we will move on to our final speaker of this session. We have Igor Polupsky from